じゃあ、大体時間ですので、インターティーンの先生もご想像くださいましたので、はい、始めたいと思います。このままチェル・アルステインさんの、博士の校長とされています。アルステインさんは、国費留学生でしたよね。ロシアからの国費留学生として、平成26年に修士に入って、それが28年から博士進学で、31年3月に、研究士の認定退学をして、それから3年経ちました。で、卒業認定退学後は技術で働いていましたけども、今はワークスアプリケーション、エンタープライズというところで、研究開発をされています。じゃあ今日は、このタイトルで次の発表をお願いします。
Thank you very much for gathering here. I would like to present what I've been working for more than 6 years, I believe. So the title is Enhancing Morphological Analysis and Example Sense Extraction for Japanese Language Learning. So the overview of this talk would be following. I will go over some basic things on foreign language learning and natural language processing, with giving some specifics on Japanese language. Then I will go into the details about the morphological analysis, giving introduction about the task, the first main improvement, which is improving analysis speed and accuracy of Juman morphological analyzer. Then I will talk about full neural unigram only morphological analyzer, and I will finish everything talking about the automated example sense extraction for Japanese foreign language learning. So, foreign language learning is compulsory in the education of majority of the countries, and it is important. While the machine translation has reached very good accuracy, there are still some problems. I will talk about them in the very end. And language learning is supported by teachers and materials. Those materials can be interactive and non-interactive. And materials are presently can be created using the techniques from natural language processing. So I want to focus on the vocabulary learning. It is a crucial step of language learning, and it requires substantial time and effort. Basically, it requires each learner to understand the word itself and understand its contextual usage. And example sentences are very useful for this context. Having automated high-quality example sentence extraction would be a very useful tool for vocabulary learning. And the focus on this thesis is on Japanese. The thing with Japanese, it doesn't have natural word boundaries as a lot of language have, and NLP applications need to segment the text without boundaries into words, and those words should be natural and human-defined. This process is done by morphological analysis, and their accuracy is very crucial for any educational application. So, morphological analysis. Basically, we need to perform the following with a human-defined segmentation standard. Usually, it is word segmentation, partial speech analysis, maybe reading estimation, lemmatization, and some other tasks. There are two main approaches here. I probably have some bugs with because some text sometimes doesn't show up. And I don't know why. should be like this, not like that. Non-supervised approaches to there exist non-supervised approaches to the word segmentation. For example, sentence piece. Still, human-defined standards are important in when the UI UX is word-based, for example, full text search, for educational applications, and I believe for explainable AI applications. So, for example, in Japanese, tokens which span one-set boundaries are very unnatural, and a sentence piece can produce those kinds of tokens. There are two main types of approaches for the morphological analysis. The first type is lattice-based analysis. The tools or approaches which use this type of approach are Rakkyo, Juman, and the tools which are similar to them, and transition-based approaches are also, in my opinion, are sort of lattice-based. The point-wise approaches are a bit different. I will talk about the both types of approaches in a second. First, on the lattice-based. In these approaches, we build a lattice which contains all the word candidates and paths between them. And we score each path through this lattice. And the path which has the highest score becomes the answer. So for scoring, there are different methods. So Juman has manual tuning. Some methods use HMM. Amicab and its derivatives use CRF. Juman++ use perceptron family. It's possible to use neural networks, but it will be very slow and it will take a lot of time to analyze a large number of text. On the other hand, there is point-wise analysis. In this case, we make a decision on each character boundary, whether it starts, for example, a new word or not. This kind of approaches is used very often in for Chinese word segmentation. For Japanese, Qt uses support vector machine and binary decisions like this. So if we compare them, this kind of approaches, lattice-based approaches need some kind of dictionary to achieve high accuracy. And they need to search through a direct graph, which can be a bit slow for the analysis time. If we use only background features, the Viterbi search through this graph will give optimal results. If we use features which are not backgrounds, we need to do beam search, and any search will become an approximation. And it is relatively easy to get and best analysis from this kind of structure. And for the present, it seems that for Japanese, it's possible to get better accuracy with this kind of approach. For the second, the dictionary is not required, but it helps to increase accuracy somehow. You don't need to do the search, so this kind of analyzers can be very fast. However, it is difficult to use the dictionary features like part of speech and other features which are not present in the surface, and it's impossible to get any best results from these kinds of courses. So they have their pluses, they have their minuses, and so the first contribution of the thesis are improvements of Juman++ morphological analysis. So what is Juman++? The main idea is to use a recurrent neural network language model in addition to other models to consider whether a segmentation makes sense or not, basically. So what is good about Juman++ is its accuracy. So when we have trained a large language model on annotated text corpus, we have achieved a great improvement in accuracy and really have reduced a number of errors, which segmentation errors, which don't make any sense. But the problem with the original Juman++, it was very slow at the length of unusable. So the Juman++, the improvements of Juman++ made it possible, made the Juman++ actually usable while gaining some points on the accuracy as well. So why did it become faster? There are a lot of reasons. They can be divided into algorithmic and microarchitectural improvements of the Juman++. So many algorithmic improvements are the really good customized dictionary representation and removing non-necessary computations and reduce search space. I will talk in detail about these 2 points. On the microarchitectural improvements, we've been using cache-friendly data structures, for example, structure arrays layout for lattice and nodes. We have used code generation for the branch-free feature extraction and other more and a lot of implementation tricks, which in result helped us to achieve that kind of work. So before talking about the dictionary improvements, I need to explain a bit about the Juman++ model. So it is a lattice-based analyzer, so it assigns a score to each path through a lattice, and the scores are assigned using the linear combination of a linear model and recurrent neural language model. So the main score of this path using the model uses the computation of a linear model. Those features are computed using uni, B, and trigram feature templates, which use, for example, part of speech in the different granularity, the surface of the board itself, and other strings. And we need to compute these kind of features from a lattice very fast. So for dictionary, there are some other requirements. Dictionary should be memory mappable, so it should be possible to load it from the disks, and that loading should be almost free and cacheable by the operating system. We also want to compute those features by hashing. Thus, we want to use integers instead of string representations without touching the string representations directly most of the times. So this is the original structure of the dictionary. It has some keyword with some kind of dictionary features like this. We, for each column, first the duplicated entries then we prepend the length of those entries and flatten those representations like this. And the column entries become indices into this flat representation. This gives us this integer representation of these strings, and we can use the dictionary representation itself becomes like this, and we can use these integer representations instead of these strings to compute the feature hashes. One additional thing which we win from this representation is the decreased dictionary size, which compared to the, for example, original Juman++, it is something like 3 times smaller. So this structure of the dictionary, in addition to the fast hash function implementation, gave us the first 8 times speed up over the original Juman++. The second part is about the speeding up the search through the lattice. There could be a lot of paths going through the lattice at any possible time. We are considering this boundary, and most of those paths really do not make sense in context. However, so we want to consider only paths which make sense in the contexts. Because of that, instead of keeping the global beam, the local beams for each node, we keep the global beam for the whole boundary, and use and score also the right nodes of the boundary to trim the paths that shouldn't use any sense. This is the overall sketch of the algorithm. It is described in the full detail in the paper, in the thesis. So by doing that, we have achieved speed up about 4 times in addition to the first speed up. However, there could be some, because of this aggressive trimming, there could be some problems with the accuracy. So we have done experiments. If we modify the parameters of the beam trimming, how the accuracy will be changed. The top line right here is not to use this aggressive beam trimming and use the regular beam search. So for some parameters, of course, there exists significant gap between these two accuracies. However, it's possible to find the computation of parameters which doesn't have that accuracy gap. And we are using the combination of parameters which doesn't have this accuracy gap. So finally, on the language model, Juman++ version 1 had implementation of a language model which basically was non-patched and non-vectorizable. In the Juman++ version 2, we have used the Anchor library for vectorization. We have also batched the whole computations of the RNN-LM when it's possible, and we have done the duplication of the paths which has identical neural network states. And finally, we only evaluate paths which have remained in the beam at the end of sequence token. So that's on the implementation of the on the algorithmic side, I want to talk a bit about the low-level optimization. So modern computers have this kind of memory memory architecture when the access to the different parts of the caches have greatly different costs. So cache misses are really slow, and because of the nature of hashing, most of the access to the neural model parameters are random accesses. So most of them are cache misses. So to improve this, we have tried to reduce the memory accesses as much as possible. So we have changed the algorithm to prefetch the next iteration of the feature weights, and we have reduced the number of score computations as much as possible by reordering the computations in that matter. So in sum, these improvements and some more gave us 250 times the analysis speed over the version first. And while Juman++ version 2 is slower than Juman, it is much accurate and it's actually usable while having the high accuracy. So this is the conclusion on the Juman++ part. It is fast diagram, feature, and recurrent neural network-based morphological analyzer, which is usable as a library. It is not hardwired to the Jumandic. It can be used with other dictionaries and segmentation standards. It achieves state-of-the-art on the Jumandic-based corpora. It has small model size for relatively small model size for lattice-based models, and can use surface features, which, for example, Minicup can't use. And finally, it can be used to be trained with partially annotated data, which is very useful for actual applications. That's all on Juman++. If somebody have a quick question here. Okay, I will then I'll move to the next part. So the second the second proposition of the thesis is experiments on a fully neural Japanese morphological analysis. Why did I do this? So the morphological analysis models use a lot of features like dictionary, part-of-speech tags, character anagrams, and in the case of neural networks, the embeddings of those features. And because of this, models can become pretty large, like hundreds of megabytes, or neural network models can be gigabytes. And in some cases, a model deployment can be a problem, for example, for mobile, to be able to use the morphological analysis on a web page and have it execute inside the browser. Or serverless architecture, for example, is pretty crucial. Startup type is pretty crucial on the image sites. So we would like to try another approach to this. So try a point-wise approach. Otherwise, pure neural network will be too slow to be usable. And the model should use only character unigrams as input without any additional information. We would like to infer the segmentation and part-of-speech tags using a straightforward model. So here is the model that we used. It is for each input character, it embeds in the vector space, passes it from the through the encoder, gaining a shared representation, and from the shared representation, it independently and at once infer all of the tags without doing any search. We have used two types of encoders here: the stacked bidirectional LSTM and self-attention network. If we try to evaluate this purely on the human annotated gold data, which has relatively small numbers, it doesn't show good results. It's really bad. So what do we have we tried to do? That is try to model to learn the lexical representation from huge bootstrapped corpus. We have used Juman++ to analyze a huge corpus and use that automatically train data to create to train a model on large number of automatically analyzed data. So if we do that, we have achieved the accuracy on par, or sometimes slightly smaller for leads corpus with our approach, and on Kyoto University corpus, it's the accuracy are comparable, but it's a bit slower. But baseline is already very high here. On the other hand, the neural network models are really small. For example, here they are like 15 megabytes compared to the 400 megabytes for Juman++. So we have performed additional experiments on the self-attention architecture, whether it is possible to get even smaller models without damaging accuracy much. So we have done the ablation experiments modifying these parameters of the self-attention network. So these are the first graphs. The red line is the Juman baseline, and we modify embedding dimension versus common representation size here. So from the first graph, we can see that the embedding dimension matters, but it doesn't matter that much than the common representation size. So the self-attention remembers most of the data inside its parameters and not inside the embeddings. This experiment is trying to make the model very smaller. And the interesting thing here, that the model still works until the hidden dimension of the self-attention network gets to 2. So it really starts to break only here, while being relatively stable over all of the range. So it's possible to have a mode when where the model will be really small, like 500 kilobytes, which should be at the same time usable in a web page and having high accuracy. So In the conclusion for this topic, it is possible to achieve state-of-the-art accuracy using a neural network-based model that uses only character and grams. However, it is necessary to use a large training corpus in this. Acquired models are very small, and when sacrificing some accuracy, it's possible to decrease the model size really smaller. And it should be possible to perform the dependency parsing in addition to to morphological analysis for this task. So that's all on the morphological analysis. From this point and onward, I would like to talk about the automated example sense extraction. I'm sorry. Okay. So I was talking in the introduction. I've talked a bit that learning vocabulary is important, and to be proficient in a foreign language, we need to study a large number of words, and that example sentences are helpful to every action we do to study words. So, I would like to define the goal of this task. So we want to have high quality example sentences, and by high quality, I mean these things. At the first, we do not consider sentences one by one. We consider a set of example sentences as a goal, and we want for that set to achieve two things at once. First, to have high intrinsic value for each sentence. So it shouldn't be a garbage sentence like fragment or something. It should have a representable usage of a target word. It should be understandable by a learner, and the sentence should be grammatical. At the same time, the whole set of example sentences should have high diversity. So sentences should contain different usages of a target word, and they should contain distinct words. I would like to introduce a couple of related work here. The first one performs a semi-automatic example sentence extraction for crafting a dictionary, and it has a really good definitions criteria for reference example sentences for words. The second word has really good definition on why the diversity is needed for example sentences, and it introduces an approach to perform extraction of sentences, but it uses a parallel corpus, and we want to do it from monolingual one. So the whole architecture of the example extraction is shown on this slide. We have a raw corpus. From this raw corpus, we analyze the sentences, by doing morphological analysis and dependency parsing, and we put them inside a search engine. The search engine is distributed, so it can handle really huge corpora. And it can use the dependency information in addition to the usual word information, the general search engines use. So it is possible to use this search engine to find sentences which have rich syntactic structure around the target word. So So by doing that, we create example sentence candidates. So, and from those example sentence candidates, we extract 10 to 15 the high quality example sentences. The process of example sentence selection is shown on this slide. We assign a vector similarity feature vector for each sentence and similarity intrinsic value. And we use those vectors and values to select sentences which are at the same time good and non-similar at the same time. To do this, we use the framework which is called determinantal point process. It is a probabilistic method for modeling diverse data sets. And for this definition of each feature, if its elements are computed as a dot product between the similarity features multiplied by quality features, the probability of sampling a subset can be computed is proportional to a determinant limited by the selected items. And it assigns higher probability to non-similar subsets. In computation, it is possible to avoid the explicit computation of the whole kernel and to have a greedy selection algorithm which still has good algorithmic bounds on the diversity of the set, to have the computational complexity being linear in the number of the candidate items, which is very useful for selecting from selecting items from a large set. So for similarity, we have used three kinds of features. Our objective is to measure how two sentences are similar in their relation to a target word. So there are three main facets of this similarity. Lexical, so whether the word, whether two sentences have a simple word overlap. Syntactic, so whether the two sentences have similar semantic structure near the target, and semantic, whether the target word is used in a similar set, whether a target word used in two sentences in a similar sense. We were using a vector space model with non-target words with TF weighting for the first feature. The second, using also vector space models, but it used partially part-of-speech array subtrees for this, and the third one uses dense representation of sentence similarity based on the broad type projections. Using similarity features and some other things, we also have the value features. First value features is centrality, so they represent how close a sentence to some kind of mass of other sentences. We use a similarity to a nearest k-means centroid. In this case, for semantic and syntactic vectors. The second thing is semantic cardinality. So whether the size, so it is based on the size of k-means clustering. The third one is a difficulty relative to a learner. So which we compute based on the word difficulty. For our experiment, we set it for something similar to GLPT at 3 level. And the final is rule-based goodness measure, which demote really bad sentences, for example, sentences which contain a lot of katakana. So for evaluating this part, we have performed human evaluation experiments with 23 learners and 1 native teacher of Japanese. We compared our method to 2 baselines. The first is a baseline which I have introduced in the related work section, and the second is a random selection. We adopted 14 words for this test: 5 verbs, 3 adjectives, 3 adverbs, and 3 nouns. All words were having several sentences, so to check whether all of the methods can cover multiple senses for the word learning. Participants were asked to select a list, a list of sentences from either of the methods, which they thought to be the best. And teacher was additionally asked to rank appropriateness for the learners of GLPT N3 and 2 levels. We have performed all the experiments in an interview manner because we wanted to evaluate whether our criteria for designing this system was correct. So we have, so I have asked all participants to explain why they have performed a method over other methods, and I didn't give any participants explicit criteria. I've asked participants to formulate their own criteria and to check whether the criteria of the participants were matching with my criteria when designing this kind of algorithm. I will talk on this later. So first part is quantitative evaluation. So so right here we have words of learners for each method. Basically, all the learners have preferred the proposed method over other methods, and especially for the learners of N3 and N2, they strongly preferred the DPP over other methods. These stars mean that the result is statistically significant, larger than the 50% or statistically significant larger than the 33%. So here is a general feedback on from the learners of the method. So for DPP, the learners generally said that it was good that it produced short sentences. It generally gave different usages. There were no useless words. It was possible to guess the meaning of a target word from context. The sentences looked good. They were close to daily life. On the other hand, learners, especially high-level learners, have said that sentences were short and bland, and some sentences could contain both compound and non-compound verbs, which was confusing. Some sentences some sentences, especially for high-level learners, were pretty similar and got that kind of negative feedback. For the Mello, it generally contained different usages and different grammatical constructions, but there were a lot of sentence fragments. It contained difficult grammar, especially for learners of low levels. They could look very informal, and some learners really didn't like that kind of sentences as example sentences. They were difficult to read fast and had similar sentences sometimes, had really bad things like bad punctuation. For the random extraction, there were different sentences, interesting usages. Sentences were pretty long and had a lot of context. But on the other hand, they could have had too much Katakana words. Sentences could have been very long, which was good for high-level learners and bad for low-level learners. They could contain difficult words, and they often have contained words which are not useful for examples. And some learners, for example, really didn't like emoticons, kaumoji. They really didn't like that example sentences have contained kaumoji. So, regarding those results, some more analysis. So we tried to validate our criteria, and first criteria is diversity. The diversity is important for selecting example sentences, and almost all the learner participants have said that independently have said that the diversity was important, and they have used that criteria to select Lisbon lists. The second part is difficulty. Our definition was that the sentence shouldn't contain words harder than the target word. There was some agreement on this state, mostly by people who have used flashcards, and non-flashcard users sometimes disagreed. And at the same time, on the learner level, the low-level learners have preferred the easy sentences, and high-level learners have found the easy sentences to be non-interesting and plain. So the second thing is the criteria of interestness. So a lot of learners have preferred lists which contained an interesting sentence. We have selected some group of the sentence interestness. For example, whether the sentence was interesting to the participant itself, so whether it had some kind of vivid image, or it had some kind of story. So, to conclude this section, we proposed and implemented a new method to automatically extract example sentences for language learners. And as a result of automated population experiment, the learners have strongly preferred our system to other systems, especially students of entry level, which we have targeted our system to. So as a future work for this session, it would be very interesting to improve the sentence difficulty estimation and improve semantic similarity vectors. While the current implementation of these two currently work, they could be much better and give much better results. So to conclude the whole presentation, one of the adversary for language learning is machine translation. Like, if the machine translation become very bad, you don't need to learn any languages. However, it's pretty still not that way, and it's pretty easy to break machine translation. It's my personal anecdote. I have a daughter, and my mother usually, and we upload a lot of pictures and videos online, and my mother writes a lot of comments in Russian. And my wife tries to use DeepL to read those comments, and oh boy, that is so bad. Like, unbelievably bad. It will take a lot of time to fix those kind of emotional sentences, to pass emotions correctly through the machine translation, for example. So we have proposed and implemented tools, a set of tools which can greatly improve the experience of foreign language learning. So the morphological analysis tool I believe, will greatly improve, especially the next generation of NLP tools, whether they're educational or maybe other. And automated example sentence extraction will, I believe, it will improve much more better personalized high-quality language learning. So these are my list of major publications which form the base of this thesis and some other publications. Thank you very much.
Okay, thank you for the presentation. So before moving to question answering session, you participated in the design school. So I want to please explain a bit about your design school activity, what you learned from the school and design school, what you learned from design school, how to contribute to this business process. Please explain briefly.
Well, activity in the design school have taught that a lot of that kind of design is based on the trade-offs. So you need to sacrifice something to achieve something. For example, for morphological analysis, we sacrifice some analysis speed to achieve better accuracy. Or we can sacrifice training time to make models smaller for the section. So making those kinds of trade-offs to be correct is what leads to a good design in probably any case, I believe.
はい、じゃあ、質問、まず先生。
はい。
彼は日本語
はい、質問は英語でも日本語でも構いませんので、お願いします。どちらでも大丈夫です。じ
ゃあ、まず最初のパートなんですけど、
はい。
まず自慢クラスは RNN の部分だけいうのが大きなポイントですよね。
まあ、
いろいろいっぱいあると思うんですけど。
はい、大きなポイントではありますし、RNN は確実に精度には貢献してますけど、売りにトライグラムまでのモデルもそれほど、 それほど劣ってはないですね。
僕が聞いてた、my question was,
はい。
what the improvement, difference in the improvement using RNN compared to the trigram?
Compared to
Trigram.
trigram.
それが、トライグラムがそれ。
I don't have bar here without the trigram. It is in the thesis, but the accuracy of the Juman without the Juman version 2 without the language model is somewhat similar to Juman version 1 with the RNN, because the trigram model has become a bit more rich in the version 2. So the difference between them exists, and it is larger on this corpus because we have used the web corpus for language model pre-training, I believe. It is really the same, but I believe that the main objective of our language model is to smooth out the trigram model, which can be pretty rough at edges, and RNN serve as a smoothing argument.
Okay. So in summary, the improvement, what is the improvement of using RN of a trigram in terms of accuracy? And compare the Apple one versus green one, or
I need to look it up in the thesis, but it was something like 0.2% for the Kyoto corpus, and 0.1 or 0.2 for the Kyoto corpus, and 0.4 or 0.5% for the lit corpus. It exists, but it's not very large.
so there are more difference between the diagram and trigram.
Yes, there are some cases which are not possible to analyze without the trigram, but we haven't tried in a bigram only mode. But the MECAB can be seen as a best implementation of bigram only mode, I think.
Yeah. So can you just ask the green one use also the RN? The green bar
Yes.
using RN.
You mean the version 1 using RNN only, or?
I don't know. So I'm asking. The green one, what language model does the green one using? 緑のやつはどの言語モデルですか？
緑のやつというのは Juman++ バージョン1でいいですかね。いや、V1 と V2 の言語モデルの実装は完全に一緒です。
言語モデルは何ですか？
言語モデルはミコロフが定義した言語モデルです。それは RNN プラス、RNN の言語モデルプラストライグラムのマクシマムエントロピーの言語モデルの足し合わせのモデルのジョイント学習です。
あ、そっか。紫もそう。
はい。ニューラルネットワークだけでは試してないです。
あ、そっか。そのリングはどっちの方がウェイトはどうなの？トライグラムとニューラルのウェイトは
言語モデルの中身に言うと、あれは分割することはできないですね。あれは、 重みではなくて、ジョイントのモデルですから。
わかりました。だけど、RNN だけだったらやっぱりうまく動かない。
強い LSTM みたいな言語モデルはおそらくうまくいくと思いますけど、問題は重いですね。こういうところも速度とのトレードオフは激しいと思いますから、なかなか難しいところです。
はい。じゃあ、2つ目のところなんですけど、39枚目のフライです。39。
Okay, it's faster. はい。
はい。ここ、よくわかんなかったな。よくわかんなかったんですけど、はい、ゴールドからシルバーで良くなってるじゃないですか。
はい。
はい。そこは、そのトリックは、データも増えてるんですか？データ量が。
ここら辺はデータ量は圧倒的に増えてます。
どれぐらい増えてるんですか
？10倍ぐらい。ゴールドだと、兄弟コープスとリードコープスのゴールデータを合わせて5万分くらいですね。ここは5億です。
まあ、1万番ぐらい。
はい。だから1万倍増えてます。
まあ、だからデータ量が増えてるから、性能が良くなったんです。
はい。それはそうですけど、このモデルは辞書を使ってます。このモデルは辞書を使ってないです。
それは分かってますけど、ゴールドからシルバーが良くなった理由は、
はい。
データ量が増えたのが一番。
はい。戦略はデータで叩くことでしたかね。
だから、入力はたくさんデータがないと。
難しいですかね。というのは、それは私のニューロンに対しての意思です。
わかりました。それスピードはどうなんですか？コメントのスピードが。
ここら辺の速度は、頑張らなかったのでなかったんですけど、頑張って実装すれば10万プラスプラス並みの速度が出ると思います。
普通にやったらどれぐらいですか？
テンザーフローの実装は1秒では1000分くらいはいったかな。けれどそれは GPU を使って。CPU は、GPU の10倍の力くらいじゃないですかね。並列しなくて。頑張れば CPU での速度は10万プラスプラス並みでいけると思います。もちろんいろいろトリックを組む必要がありますけど。
で最後なんですけど、
はい。
今、なんだっけ、JLP、JLPT の N3 とかをターゲットにしてるんでしょうJLPT のテストです。はい。N3 をターゲットにしてる。
N3 をターゲットにしてる。
レベルをN1 とか N2 とかにしようとしたら、なんか他のパラメータを変えたりできる。
はい、できます。この難易度の項目は、比較的に難易度だから、推定難易度から、近ければ近いほど、スコアが高いというものだけで、設定すれば、N2 とか N1 に設定もできますが、実験は N3 当てにしようと思ったんですけど、それぞれのレベルに対して実験は、可能ですが、結構、大まかな実験をする必要がありますから。
いや、別に実験をする必要はないんですけど、 いや、使いたい、そこをタイプしたいからどうすればいいかっていう。
このレベルは、変えられます。もっと低いレベルではおそらくうまく動かないと思いますけど、N3 より低いレベルの例文は自動的に作るのはなかなかできるもんではないと思います。
それは何
使われている日本語は独特すぎる。
わかりました。ありがとうございます。ありがとうございます。
ありがとうございました。
じゃあ、私も評価実験のことで教えてください。まず、クライテリアを与えないで選んでもらうのはどうしてですか？
システムの構成の中で私たちの過程と実際に学習者のニーズはマッチしているかということを検証してみたかったです。
この実験の時に、まずリストを選んでもらって、それからそれがどのメソッドに基づくものかを評価者に教えてあげたわけです。
評価者に教えていただいてたんですね。評価者が3つのリストを読んで、どのリストが一番良かったかを教えてくれてたんです。
そしてその選んだものがどのメソッドによるかを評価者に教えてあげたわけです。
教えてないです。
教えてあげないで、ただ選んでます。
評価が全てが終わってから教えたんですけど、
理由を説明してもらう前に教えてあげ
た。実験の理由を教える前に、この手法はこれで、この手法はこれで教えたんです。実際に実験をやってもらった知り合いが一人後ろにいます。
どうして選んだんですかっていう説明をするときには、そのリストがどうやって作られたかは教えられてない。
すべての手法には、これは手法 A、手法 B、手法 C というラベルだけが。
なので、どうやって作られたかは教えられてない。そして、参加者は自分で57ページにあるような、これは理由ですか？参加者が理由だと。そして、これは、実際に作った時のクライテリアと合致してましたか？
実際的にクライテリアについては、ここら辺は、これは、全体的なフィードバックで、実際の一つ目のクライテリアは多様性で、それは完全に一致してて、難易度、それは部分的に一致してて、そして面白さは、それは考えてもなかったんですけど、そういうクライテリアは結構ありました。
なるほど。そして、例えば、評価者の側の考えてたクライテリアというのは、今後入れていく可能性っていうのはあるんですか？
面白さを入れたら結構学習者のモチベーション、学習に対してのモチベーションが上がるんじゃないかなという仮説があります。これは結構改善の方法として一つがあります。
ここでグッドとかバッドっていう評価がありますが、それはどんなルールで作られた評価ですか？
これは普通に、学習者の評価です。
学習者がこれはグッド、これはバッドだという形で評価した。そしてそれに基づいて、それがインタレスティングというクライテリアだということを考えたと。K さんの研究ですけれども、5年後、10年後、おそらくこの領域発展していくと思いますけれども、その時にこの研究はどういうような学術的、アカデミックな意義、あるいは応用的なアプリケーションとしての意義を持つと。
応用的な意味ももちろんですけど、機械翻訳のシステムは非常に素晴らしいものにならない限りは、言学習は消えないし、そして、言学習者は誰でも効率よく学習したい気持ちは結構あります。 けれど言語解析にもこういう感じの文の面白さみたいな、これは結構基礎研究として非常に面白いかつ難しい問題だと思いますので、こういうところの課題も解決しなければいけないと思います。
で、実際にこれ N2 や N3 の人にとって評価が高かったですよね。インタレスティングは、これは、N1 の人たちにも評価が高いわけですか？
この評価に行くと、結構、N1 の方は、ランダムは結構高かったんですね。なぜランダムが高かったというと、文がある程度長くなっていて、長くなっていれば面白い文の入る確率が高くなるだけで、完全に面白い文を探すのではなくて、ただ確率的に出る可能性は高いんですけど、この実験もちょっとこのランダムも完全にランダムではなくて、例文候補からのランダムなんです。例文候補も全ての文ではなくて、ターゲットワードあたりで文構造がたくさんの例えば動詞の場合はたくさんのアーギュメントを持っている文があったんです。もともとなんで。だからランダムも完全にランダムではないです。検索のバイアスがかかってるから結構面白そうな文が出る確率は高かっただけで。そういうこともあると思います。質問の答えになっているかどうかわからないんですけど、すみません。
はい、ありがとうございました。じゃあ、実際に実験に参加する。
はい、今あるんですけど、28ページ。
はい。28。これですね。はい。
ローはどれだけ、なんでしょう、文を長くするかだと思ったんですけど。
ではないです。ローは、ローは、どれだけ左の候補と右の候補を残すかみたいな一つのパラメータにしたの。
長い方が精度が良くなると思ったんですけど、そうはならないですか？
これは、テスト時のローと学習時のローの曲線なんですね。学習時よりテストが高ければ、それは悪いんです。例えば、1、学習時よりテスト時の方が少なければ、それは悪いです。テスト時はある程度のビーム幅を持ちながら探索しているので、トレンジに、テスト時にそのビーム幅を削るとあるはず、テスト時として、あるはずだったものが消えるから、こんな風に精度が下がります。増やすと大体上がります。
詳しくないので、素人質問だったらあれなんですけど、これ同じにすべきじゃないんですか、トレインテストで。
なんで実際のパラメータは学習の時はこういうことに学習の時は1個小さくしてます。トレインの時にやっぱり学習になかったものが学習の時とテストの時は学習の時になかったものが出てきますから、少しだけ融通が利くビームハブを少しだけ広くはしてますけど、もちろん小さくするのはダメですけど、ちょっとだけ大きくしても大丈夫で、そして ここで見せてるようには、実際には学習よりテストの方が高ければ、そっちの方がいいです。
いや、これ僕もおかしいと思ったんですけど、
はい。
動画2の時が、このグラフ見て一番いいじゃないですか。
動画2はこれです。
それが一番いいじゃないですか。
あれあれ動画2はこれです。
そうそうそう。
はい。
それは僕も全部分かってるじゃないですけど、僕の推測では、1番目は絶対必要で、当たり前ですけど、1番目も結構まともな候補が出てるんだけど、3番目以降は間違った候補が出てるから、多分悪影響が出てる。
大きくすれば悪影響はするほど出ない。
でも2がそれだけど、よければそれは作れるからいいんだけど。
けど、それでも、2の、例えばテストの方が2で、トレインの時は2ですが、テストの時は5、6くらいは必要になります。
テストはひどいのが間違いんだけど、トレインの時にひどいゲームをすると、間違いの候補が出てくるから、それは悪影響になる。
悪影響はなかった。
でも、4、5、6だんだん悪くなってる。
4、5、6の唯一比較できるのはここら辺ですからね。
だけど、カーブを見てもそんなに4、5、6を使う意味はこれから見るとないです。
6は本当にこの高さの方に来てますからね。1してればいいんですけど、大きくすれば、トレインの方は、ある程度幅があった方が良かったと思います。
ありがとうございます。
はい。
もう一点だけ、
はい、
最後の今後、フューチャーワーク的なところで、機械翻訳の場合に感情的な文の翻訳が難しいっていうお話をされたじゃないですか。
はい、
この例文はそれは対応できそうなんですか？
どうでしょう。例文ですか？
最後のプロポーズドメソッドで分かりやすくない。学習者に分かる文を出すっていうじゃないですか。
そうですね。結構面白い質問ですね。モノリンゴールで感情差を判定する方が簡単だと思います。翻訳するよりは。感情が入ってるか感情が入ってないという判定の方が簡単だと思います。モノリンゴールでは。だから対応しようと思えば、モノリンゴール対応はもっと簡単にできると思います。答えになってるんでしょうか？
今回使った例文があったじゃないですか。
はい。
楽しいとか嬉しい、悲しいのような感情的な言葉はあまり入ってないしたので、
入ってなかったんですけど、
そういうものを入れると難しくなるのかなと思ったんですけど、機械翻訳よりは簡単という感じなんです。文の生成自体はそんなに難しくない。
ここは文の生成はやってなくて、文の選別してますから、生成はやってないです。どうでしょうね。母が書いてるものは、それは別に、楽しい悲しいが入ってるんではなくて、ロシア語の書き方は独特すぎて、感情がこもってるから、機械翻訳機が壊れています。それは結構 なんていうか、タンク入ってるというよりは、本当に書き方のスタイルは完全に違いますから。
いや、そうだと、この日常的に使うような言葉を出すのはやっぱり難しいのかなと思ったので。
まあ、うん。まあ、うん。まあ、すみません、ちょっとわからないです。
いや、はい、大丈夫です。すみません、いいな。はい。
クリエイターソフトウェアに組み込めるという話、クリエイターソフトウェアに組み込める話、重要だという話なんですけども、現在もほぼ完璧な制度にっていうくらいなんですけども、そこで例えば大規模なファーストで購入されたもうパートみたいなこのモデルを使ったさらなる構造が可能でしょう
バーッとの難しいと、そういう感じのモデル、大規模のモデルの難しいところはすでに単位がありますから、単位の決め方がすでにありますので、携帯使いすぎみたいなタスクにはあんまり向いてないと思います。
サポートなんですけど、でもキャラクターベースで切ってやるというのはあるかと思います。
はい、私はちょっと、携帯使い式の実験ではバートみたいな保管補助タスクを追加して学習してみたことがあります。入れない方が良かったです。ある程度データの希望が大きければ、そういう補助タスクがいらなくなるだけで、バートの良さは、事前学習して、そしてファインチューニングとして使うものだと思いますから、そういう感じの事前学習の知識、表現を作るということで、ある程度のデータ学習があれば、そういうこと自体がいらなくなりますので、さらなる改善は、結構、現在に残っている問題は、ゴールドコープスの対象外の問題とかコープスがうまくキャプチャーできてない言語現象とかの方が多い気がしますから、そういう言語現象を的確に潰していけば、改善できるんですけど、そういう現象は結構少ないので、コーパスを大幅に増やしてもそれほど精度が良くならないと。結構的確に現象をピックアップして潰していくしかないと思います。改善しようと思います。
はい。はい。じゃあ、これで終了したいと思います。
ありがとうございました。